In a perfectly controlled environment, solar physics operates with beautiful precision. Photons excite electrons, and you get a steady, uninterrupted flow of pure energy. But we rarely deploy solar panels in perfectly controlled environments. We put them on residential rooftops. They face different compass directions, sit at varying tilt angles, and contend with unpredictable moving shadows from trees and chimneys. Despite these chaotic variables, the standard industry installation groups all of these panels together. They are wired in a continuous sequence, pooling their voltage to feed one centralized string inverter mounted on the side of the house. Treating a messy, dynamic rooftop as if it were a pristine laboratory environment creates a severe structural bottleneck. This animated blueprint shows why. In a traditional series circuit, Kirchhoff's current law dictates that the electrical current must remain constant throughout the entire loop. That creates the Christmas light effect. If a single cloud or chimney shadow drops the energy production of just one panel, the current flowing through every other panel in that loop will instantly choke down to match it. A shadow covering a mere 5% of a single panel's surface area can trigger a massive, disproportionate loss of power across the entire array. A centralized architecture ties the maximum potential of the entire system to its weakest performing component at any given second. The solution is to remove the central box entirely. By shifting to module-level power electronics, we mount a miniaturized inverter directly onto the back of every individual panel. Relocating the hardware reconfigures the system at its most basic level. It shifts the entire array from a dependent series circuit into an independent parallel architecture. This schematic of a parallel circuit shows the immediate advantage. If dirt, debris, or a shadow limits the output of one panel, the adjacent panels ignore it and continue pumping out their maximum capacity. Eliminating the central bottleneck allows the system to capture the actual mathematical energy capacity of the roof space, regardless of the orientation or shading of specific modules. But isolating the hardware is only half the equation. Decentralization gives each panel its own onboard processor to actively manage its unique microclimate. This chart plots a solar module's current against its voltage. Because irradiance and temperature constantly shift, the exact point where a panel produces its maximum power fluctuates wildly throughout the day. The microinverter uses an algorithm called maximum power point tracking. By rapidly testing tiny voltage adjustments, it uses a perturb and observe method to locate and pin itself to the absolute apex of power extraction, second by second. Field data confirms that when every panel runs its own independent tracking algorithm, total system energy yields increase by 5 to 25% over centralized string setups. Solar panels transition from passive energy collectors into highly active, intelligent optimization engines. This thermal illustration highlights a severe engineering paradox. Heat is the natural enemy of complex power electronics, yet microinverters are designed to be bolted directly beneath solar panels on a baking roof. To test their endurance, researchers subjected 40 microinverters to an accelerated thermal stress test. The units were continuously baked at temperatures between 65 and 75 degrees Celsius for 15,000 hours. This Weibull distribution chart maps the results. Over those thousands of hours of extreme thermal stress, the units recorded 0 failures. When applied to the Arrhenius life stress model, that data projects an operational field lifespan of 24 to 48 years. The power electronics will comfortably outlast the 25-year warranty of the solar panels themselves. Conquering this thermal degradation makes distributed power conversion a highly durable, long-term infrastructure investment. Beyond efficiency, there is a strict safety imperative. Traditional string systems push up to 1,500 volts of highly volatile direct current across the roof and down the side of a house, creating a severe arc fault and fire risk. Microinverters neutralize this threat by converting the high-voltage DC into standard, grid-compliant alternating current directly at the source panel. This localized conversion enables immediate rapid shutdown compliance. In an emergency, first responders can cut the grid connection and safely de-energize the entire roof matrix in less than a second. A modern energy grid cannot require consumers to choose between maximum efficiency and human safety. This transition creates a fleet of independent micro-power plants, where the survival of the system no longer hinges on the performance of a single shaded module. This granular, module-level intelligence provides the exact data visibility and load flexibility required to integrate homes into future smart grids. The microinverter provides the granular control necessary to extract maximum energy from every square meter of rooftop, regardless of environmental chaos below.